Welcome to the Deep Dive. Today we're looking into something pretty fundamental for AI agents, how they learn to actually use software like we do, clicking buttons, navigating menus on a computer or phone screen.
It's a tough area. Getting AI agents to reliably see what's on a graphical user interface or GUI and then interact with it to get things done, especially complex tasks, that's a real challenge.
And training them usually takes a ton of human effort, right?
Yeah.
Labeling screens, showing the AI what to do step by
It
step.
does, and that's where the source material we're diving into comes in. It introduces a framework called ZeroGUI. The idea is to automate that learning completely, aiming for zero human cost in getting the training data ready.
Zero human cost. Okay, that sounds potentially transformative. So what's our source for this?
We're working from a research paper titled ZeroGUI, Automating Online GUI Learning at Zero Human Cost. It's from researchers across a few universities and the Shanghai AI Laboratory. It details their whole approach, the methods, the tests.
Great. So our mission today is to unpack how ZeroGUI actually achieves this automation, break down its main parts, and see how well it worked in their experiments. Ready?
Let's get into it.
Okay, so first, maybe set the stage a bit more. Why is training these GUI agents so hard and, well, expensive?
Well, as you said, these agents need to perceive and interact. Older methods sometimes used underlying code like HTML, but the trend now is towards using these powerful vision models, large vision language models, or VLMs that just look at the screen like a human does.
Learning just from the pixels, basically.
Sort of, yes. But the main issue with the standard offline training for these VLM agents is the data bottleneck.
Offline meaning you train it on a big pile of data collected beforehand.
That's it. And creating that pile requires, well, a lot of manual annotation. Humans have to mark up screenshots to tell the agent, this is a button, that's a text box, that's called grounding. And then you need step-by-step guides, trajectories, showing how to complete tasks.
Right. Sounds time-consuming.
It is. Very expensive. Doesn't scale well if you think about all the different apps and websites out there. Plus, real GUIs change. Things pop up, layouts shift. An agent trained only on static old data struggles to adapt.
Okay. And the interactive environments people use for training, like OSWorld or AndroidLab.
They're useful for letting the agent try things, but they often lack the sheer volume of diverse, automatically verifiable tasks you'd ideally want for, say, reinforcement learning online, where the agent learns as it goes.
So you need lots of varied practice, ways to know if the practice worked, and it needs to cope with changing screens, all without manual labeling. That's the puzzle.
That's the setup. And ZeroGUI is proposed as an online learning framework to tackle this. The agent learns by doing, interacting directly in the environment.
And the key is automating that whole learning loop.
Correct. Automating task generation, automating the reward signal, figuring out if the agent succeeded, and then using that to improve the agent via online learning. The paper breaks this down into three main components.
Okay, let's take them one by one. Component one, automated task generation. How does it come up with things for the agent to do?
It uses a VLM. In their work, they use GPT-4o. They basically show it a random screenshot from the environment.
Like, here's the desktop right now, or here's an app screen.
And they prompt the VLM to suggest realistic tasks a user might perform based on what's visible. Like, based on this screen, suggest a few things someone might try to do.
How do they make sure the tasks are, useful and varied, not just click the button over and over?
They used a couple of prompting techniques. One is example-guided prompting, showing the VLM good examples of tasks for that specific environment, helps it generate similar relevant ones.
Oh, okay. Giving it a hint.
And they also ask for multiple candidates at once. Generating several options seems to encourage more diversity than just asking for one task at a time.
The paper also mentioned generating infeasible tasks. Why would you want the agent to try things it can't do?
That's actually important for robustness. It teaches the agent to recognize when a goal is impossible from the current state, maybe to signal failure gracefully, instead of just getting stuck trying endlessly.
I see. So it learns its limits, too, and they generated a lot of these tasks.
Thousands for the OSWorld environment, yeah. A smaller set for AndroidLab, too. Enough to provide a good base for training.
Okay, so the system generates practice tasks. But then, how does it know if the agent actually did the task correctly? That sounds like the really tricky part. Component 2, automated reward estimation.
It is tricky. Normally, you'd need custom scripts for every single task to verify success. That's not scalable or zero cost. So ZeroGUI uses another VLM for this they mentioned using Qwen 2.5 VL in their experiments.
So one AI generates the homework, another AI grades it.
Something like that. The second VLM looks at the whole sequence of actions the agent took the trajectory, usually represented by the screenshots captured during the attempt. Then it outputs a simple reward, 1 for success, 0 for failure.
But can you really trust an AI to judge that perfectly every time? I mean, these models can make mistakes.
That's a critical point the researchers addressed. They found these evaluator VLMs can be wrong, and specifically, false positives are a big problem.
False positives,
Mhm.
meaning the VLM says success when the agent actually failed.
Correct. And if the agent gets rewarded for failing, well, that really messes up the learning process. It reinforces the wrong behaviors.
Yeah, that makes sense. So how did they make the VLM grader more reliable, especially at avoiding those false positives?
They highlighted a few design choices. First, giving the VLM all the screenshots from the agent's attempt, not just the start and end. Seeing the progression helps it understand the state changes.
Okay, context matters.
Definitely. Second, they exclude the agent's own generated text responses from what the evaluator VLM sees. Sometimes the agent might hallucinate and say it succeeded, even if the screen shows it didn't. You don't want that misleading the evaluator.
Don't let the student talk their way into a good grade if the work is wrong.
Kind of. And third, maybe most importantly, they used a voting mechanism. They asked the VLM evaluator the same question: did this trajectory succeed? Multiple times.
Like getting a second and third opinion.
Right. And they found that requiring unanimous agreement among the votes for a success reward, a 1, significantly improved precision, meaning it cut down those harmful false positives. This led to more stable training and better final results.
Okay, that's clever. Multiple checks. So, automated tasks, automated rewards. Now the agent needs to learn from this. Component 3, two-stage online reinforcement learning.
So now you have this continuous stream of practice tasks and feedback. The agent can learn directly through trial and error in the environment. That's the online learning part. They structure this into 2 stages.
Stage 1.
Stage 1 is training on that big pool of automatically generated tasks. The goal here is to build general skills, learn fundamental ways to interact with GUIs across all sorts of different situations the generated tasks throw at it.
Building a foundation. And Stage 2.
Stage 2 is test time training. Here, the agent focuses specifically on the actual tasks that will be evaluated on the benchmark tasks. It still uses the VLM-based reward, but it's fine-tuning its strategies for those specific target goals.
So, broad learning first, then specialize for the test. Makes sense. Did they use a specific learning algorithm?
They adapted an existing reinforcement learning algorithm called Group Relative Policy Optimization, or GRPO. They had to make some tweaks to make it work well for these long, multi-step GUI tasks.
Any key modifications worth noting?
One thing they mentioned was adjusting how the algorithm calculates a penalty term related to deviating from its previous policy, the KL loss. They changed from something called K3KL to K2KL.
Okay, technical detail, but what was the effect of that change?
The reported effect was improved stability during training. It helped keep the learning accuracy from jumping around wildly and avoided some numerical problems that can pop up in these complex online learning scenarios. Stable training is pretty crucial.
Right, you want steady progress. Okay, so that's the framework. Generate tasks, evaluate success, learn online in 2 stages. How did it actually perform when they put it to the test?
They took 2 existing VLM-based GUI agents, UiTARs and Aguvis, and applied the ZeroGUI online training framework to them. Then they evaluated these enhanced agents on standard benchmarks, OSWorld for desktop environments and AndroidLab for mobile.
And the results? Did this automated training actually help?
Yes, significantly. They reported substantial boosts in task success rates for both agents on both platforms. For instance, on the OSWorld benchmark, looking just at the tasks confirmed to be feasible, the agent called UiTARs improved its success rate by about 40% relatively after ZeroGUI training. The other agent, Aguvis, saw an even bigger jump, around 88% relative improvement.
Wow, 88%. That's a huge gain from just letting it learn automatically online. What about AndroidLab?
They saw improvements there too, though maybe less traumatic numerically. On the specific subset they reported, like a 2.8 percentage point increase in success rate on one operation subset. Still, positive gains across the board.
The paper mentioned different ways of measuring success, like pass at K versus all pass at K. What did that show?
Ah, right. Pass at K measures if the agent can succeed at least once within K tries. It reflects the breadth of its capabilities. All pass at K requires the agent to succeed on every try, measuring its consistency or reliability.
Okay, capability versus reliability.
And they found that stage 1 training on the diverse generated tasks mostly boosted pass at K. It expanded the range of things the agent could do. Stage 2, the test time training on specific tasks, mainly improved all pass at K. It made the agent more consistently successful on those target tasks.
So each stage contributed differently. That makes sense. Did they mention any limitations or areas where it didn't improve as much?
They did note the overall improvement on the full OSWorld set, which includes those tricky, infeasible tasks, wasn't quite as high as on the feasible-only subset. This suggests that reliably detecting infeasibility is still challenging, even though training with infeasible tasks helped somewhat.
Understood. Numbers are one thing, but the paper also had examples comparing how the agents behaved before and after zero-GUI training. Could you describe some of those?
Sure. The qualitative examples really highlight the difference. They showed cases where the original base models without zero-GUI training would get stuck, maybe repeating the same click over and over or failing to find the right element on screen, what they call grounding errors,
Like clicking near a button but not quite on it.
or clicking the wrong button altogether. They showed an example in VS Code where the base agent failed to select existing text before typing, leading to errors. Another in a presentation app where it misclicked, or in a calendar app overlooking details in the instructions, like setting the wrong notification time.
So basic interaction mistakes or failures to follow multi-step plans.
Kind of, yeah. It seemed less robust. But the agents after zero-GUI training showed more stable and effective behavior in the examples. They'd successfully carry out longer sequences of actions.
Like the VS Code example, did the trained agent handle the text selection?
Yes, the example showed the zero-GUI trained agent correctly using throttle plus A to select all before typing, handling that nuance properly. It navigated more accurately, followed detailed instructions better, like getting that specific notification time right in the calendar example. It looked less like random clicking and more like it had learned actual strategies for using the interface.
So the automated online learning seemed to instill more generalizable interaction skills.
That's what the example suggests, yeah. More robust, effective strategies learned through that automated loop.
It really is interesting to see how they built this self-contained learning system. AI generates tasks, AI evaluates success, AI learns, all interacting with the real interface.
It points towards agents that could potentially get better and better just by using software, without needing that constant, costly human hand-holding for creating training data. It's a shift from relying purely on static, pre-annotated data sets towards more dynamic, online adaptation.
So we've taken a deep dive into zero-GUI. We looked at the problem it tackles, the difficulty of training GUI agents, explored its three core automated components: task generation, reward estimation, and the two-stage online learning. We saw the results, quite impressive performance gains.
Especially those relative improvements on feasible tasks, yeah.
And we even got a feel for how the agent's behavior changed through those qualitative examples, all based on the research paper.
That's right, sticking to the source.
So maybe the thought to leave you, the listener, with is this. As AI agents get better at learning to use digital tools completely on their own just by interacting, how might that change the way we interact with technology? And what new possibilities for automation might open up?
Definitely something to think about as this technology develops further.